Welcome to this online training about reducing compile times using fast preservation. My name is Steve. This training is available for desktop viewing as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. Here are the objectives for this training. You'll learn about what the fast preservation feature is and what the advantages are for using it with a block-based design flow. You'll then see how to set up a design and use the feature with that design. Results from the use of fast preservation are included to show you the actual benefits from using the feature. So what exactly is fast preservation? Fast preservation is a feature that works with the block-based design flows available in recent versions of the Intel Quartus Prime Pro Edition software to greatly reduce compile times. It does this by essentially abstracting away all preserved logic in a design and focusing compilation effort on only the parts of the design that have been changed or optimized. Preserved logic refers to logic and I/O resources found in the device periphery, along with preserved core logic and clock network routing. The fast preservation feature takes advantage of and requires the use of the block-based design features found in the Intel Quartus Prime software. This includes design partitioning, design block reuse, specifically root partition or periphery reuse, and partial reconfiguration. Compared to the existing preservation flow that uses the preservation level feature of incremental block-based compilation, fast preservation provides substantially shorter compile times. The amount of compile time savings is directly proportional to the amount of design logic preserved. Unlike incremental block-based compilation, preserved logic with the fast preservation feature is not even analyzed by the compiler. So a large design where 90% of the logic is preserved could see a 70% compile time reduction. A 50% preserved design can provide about a 30 or 40% compile time reduction. With these amounts of compile time savings, you can get more design turns per day, allowing you to finish the design or close timing on the design faster. And since fast preservation makes no changes to preserved logic, there is also no reduction in design performance. There is no penalty for using fast preservation, only an enormous benefit. In order to use fast preservation, your design must be set up for partial reconfiguration, or PR, or be set up similarly to a PR design. PR designs are a natural fit for fast preservation because in a PR design, you are creating a fixed, preserved periphery design called the static region, along with one or more core designs that can switch to a different design on the fly, each one referred to as a persona. Once the static region is created in the base revision of a design project, different personas are compiled in separate PR implementation revisions of the project. Compiling these implementation revisions can take advantage of fast preservation. The larger the static region, the less core logic needs to be compiled in the implementation revisions, leading to greater compile time savings. But even if you are not creating a PR design, you can still use fast preservation by making your design PR-like. Create your design with a well-separated periphery and floor plan the core logic using logic lock regions, just like what is done for PR. Separating the periphery in this way is, in general, a good practice for any design. Another benefit is that if you use fast preservation on your non-PR design, you do not need to include anything that is required for PR, such as the controller IP or freeze logic. Setting up a design for fast preservation benefits any type of design. As mentioned, setting up a design for fast preservation makes use of a number of tools and features in the Intel Quartus Prime software. First, in order to use the feature, you must organize your design into design partitions that align with the hierarchical boundaries of the design. Design partitions, referred to as PR partitions in the PR design flow, are used in all block-based design flows, and, in some cases, assigned to a physical location in the device. To use fast preservation, the floor planning of design partition logic is required. Next, the periphery region, called the static region in a PR design, refers to the top level of the design that includes the I/O, but may also include some core resources. In the Intel Quartus Prime software, this is referred to as the root partition. The root partition is the main part of the design that gets preserved in the design reuse and PR block-based design flows. Logic lock regions are the feature used to floor plan a design by forcing logic assigned to the region to be physically placed within the region. Typically, each design partition or PR partition is assigned to its own logic lock region. In the PR flow, these are referred to as PR regions. Floor planning with logic lock regions is required in order to use fast preservation, since this is what separates the core logic from the periphery. Finally, project revisions are required for the PR flow and optional for the non-PR flow to help manage the use of fast preservation. They allow you to quickly switch between different assignments and settings, stored in separate .qsf files for each revision within a single project. In order to use fast preservation, your design must be organized in either of the ways shown here. On the left is a PR design. The static region is created and compiled in the base PR revision, and one or more floor-planned PR partitions are compiled in a number of implementation revisions, depending on the number of personas desired for each PR partition. Floor-planned PR partitions that do not require recompilation or optimization are preserved using design partition preservation level assignments. Fast preservation will allow the yellow PR partition to be recompiled quickly. On the right is a non-PR design. To use fast preservation with a non-PR design, the periphery must still be designed and preserved, like the static region in a PR design. Then, a new project or project revision is set up with most of the design preserved, reusing the root partition from the original project or revision. The part of the design to recompile or optimize is placed in a logic lock region. The rest of the core logic may be placed in their own floor-planned regions, but this is not required. With the fast preservation feature enabled, only the non-preserved partition is recompiled. So in order for the fast preservation feature to engage and save compile time, 3 conditions must be met. First, the design must be in a PR implementation revision or a separate design reuse consumer project. Next, the periphery of the design must be preserved, meaning it has been set up as a static region in a PR implementation revision or a reused root partition in a design reuse consumer project. Finally, there must be at least one non-preserved core partition. If these 3 conditions are met, the feature is engaged and significant compile time savings are possible. Since they're required for all block-based design flows and the fast preservation feature, let's do a quick review of design partitions. If you are already familiar with design partitioning, feel free to skip ahead to the next section of the training. Recall that design partitions are user-defined logical partitions. Logical partitions must be aligned with the hierarchical boundaries of a design. By default, the top-level entity is a partition, referred to as the root partition in the tool, but all other entities lower down in the design hierarchy must be explicitly defined as partitions. The key feature of design partitions is that the Intel Quartus Prime compiler does not perform any synthesis optimization across partition boundaries. Each partition is synthesized as if it was a separate design. The results are then merged with other partitions. Because of this, there are a number of recommendations to follow when choosing or defining partitions, which we'll discuss in a moment. The diagram highlights this. If design blocks A and B are compiled without partition definitions, then logic tying the two entities together can be merged by the compiler if it will optimize the design. Because of this, the compiler cannot separately recompile A without affecting B, since there is not a clean break where A ends and B begins. If A and B are compiled with partition definitions, the two blocks stay completely independent and can be compiled independently of the other. This isolation through design partitioning is the key to all the block-based design flows. Here is what partitioning a design might look like. Design block B has been defined as a partition. Blocks D and E have not been tagged as partitions, so, as a result, they are part of partition B. Block F has been defined as a partition on its own. It could be a timing-critical block of logic, or it's an IP that will get added to the design later. Lastly, design entity A, since it is the top-level design, is automatically set as a partition, the root partition. Since block C has not been made into a partition of its own, it is a part of the root partition. If, in the course of updating or debugging the design, the file containing block E is changed, then the entire partition B must be resynthesized and refit. The compilation database information for the root partition and partition F could be reused to decrease compile time and retain their performance numbers. If it turns out that block E requires a lot of editing, it might be a good idea to set it as its own partition. That way, blocks B and D would be preserved and would not need to be recompiled every time there was a change in E. So what can be set as a design partition? After analysis and elaboration and the successful creation of the project hierarchy, any entity anywhere in the hierarchy can be set as a design partition. As mentioned, the top level is always a design partition called root partition. A design may have many levels of hierarchy and many instantiated design entities, but usually you will not set every entity as a design partition. To use any of the block-based design flows effectively, it's important to understand what should be set as a partition and design your partitions in such a way to get the most benefit. It's important to understand the difference between core and root partitions. A core partition is one that is made up of only core device resources, such as logic and on-chip RAM blocks, and no periphery resources, such as I/O and transceiver hardware. Only core partitions can see the benefits of the fast preservation feature. While a core partition cannot include periphery resources, the root partition can include core resources. This is useful for creating a design with empty holes that will be filled in with core partitions. You can also export a root partition for use as the periphery design for another project. This is required for the fast preservation feature. This diagram illustrates the core and periphery resources in a typical Intel Stratix 10 device. Core resources include logic array blocks, RAM blocks, and DSP blocks. Periphery resources include I/O, high-speed transceivers, and IP like the hard IP for PCIe. As discussed in more detail in other trainings and documentation, there are a number of recommendations for how you plan and create a design to get the most benefit from design partitioning. We'll touch on a few of these recommendations here, starting with the planning of your overall design. The first recommendation is to try to organize your project hierarchy for good partitioning. To do this, create a hierarchy such that the larger logic blocks are in the so-called leaves of the hierarchy tree. This gives more flexibility for partitioning, as it makes it easier to break out a section of the design into its own partition separate from other parts of the design. Also, it is recommended to create entities such that when you partition, it can lead to partitions that are roughly the same size. This is preferable to creating a bunch of small entities on the same hierarchy level. Since optimization is not performed across partition boundaries, small entities are not good candidates for partitions, since they don't give much logic for the compiler to try and optimize. Thus, a bunch of small entities limits your choices for defining partitions. The diagrams here illustrate this. On the left is an example of a hierarchy badly organized for partitioning. You can see a series of equally sized smaller blocks on the same hierarchy level, followed by a large block and then more small blocks on the same level. This design would be more difficult to break apart into partitions, as there aren't really any good candidates. All of the leaves are smaller blocks, so any time savings from partitioning would be minimal. They might be better served being optimized with the logic around them. You may have reasons in your own design to organize it like this, but you may not get the most benefits from a block-based design flow with this hierarchy. On the right side is an example of a hierarchy organized for good partitioning. Here, you see large blocks of logic in the leaves of the hierarchy. These blocks are good candidates for being made into partitions and compiled separately from the surrounding logic in order to realize compile time savings, especially with the fast preservation feature. Also notice the larger sizes of these and other blocks in the design, providing more opportunities for compile time savings if they are set as design partitions. Next, think about how blocks are organized in your design and adjust that organization if necessary. As mentioned earlier, if a design block is set as a design partition, the design blocks it instantiates, its children, are automatically part of the same design partition, unless they've been set as their own separate partitions. Remember that design blocks in the same partition are optimized together when they are compiled, so it's a good idea to group blocks together in the same partition if they are highly connected or have timing-critical paths between them. Use a parent partition assignment or put the design blocks together in a single file. As mentioned, when blocks are in the same file, the entire file will be recompiled if any of the blocks changes, forcing the related blocks to be optimized together. At the same time, you want to try to avoid grouping unrelated logic into a partition. Including unrelated logic to the main logic to be optimized in the partition uses more resources that could be used for optimization. Put unrelated logic in its own separate partition or leave it in the top level if possible. When planning for a design that will use a block-based design flow with fast preservation, try to keep as many parts of the design that use the periphery-specific resources mentioned earlier in the top-level root partition, keeping parts that use core resources in their own core partitions. Of course, some I/O-related IP, such as external memory interfaces, make use of both core and periphery resources. The core resources used by these IP should still be included in the root partition. I/O PLLs are a special case of a periphery resource that does not need to stay in the root partition. If an I/O PLL is used to clock core resources, it can be included in a core partition. However, note that it will not be able to be merged with other PLLs in other partitions to make most efficient use of PLL resources. If possible, put all clocking resources, such as PLLs, in the top-level design, or in a design block directly instantiated in the top level to allow for this merging of clock resources. Finally, any clock or high fan-out control signals that are used to drive any of the global device routing resources should originate in the top level of the design instead of from a core partition. If these signals originate lower down in the hierarchy, clock buffers are needed to bring them up to the root partition for distribution to the rest of the design. There are also a number of partition design guidelines that should be followed when creating partition logic. For our purposes with fast preservation, we'll focus on just two of these: registering partition boundaries and minimizing the number of cross-boundary paths. To create good design partitions, especially for use with fast preservation, it is strongly recommended that all input and output ports of a partition be registered. This may not always be a viable option for your design, but it can make your work a lot easier later on. Registering inputs and outputs ensures that critical timing paths remain within a single partition. This means the delay between partitions will only consist of routing delay, with no logic crossing partition boundaries that would require optimization. This serves to make your partitions timing independent, loosening any placement restrictions with respect to the location of other partitions and increasing the effectiveness of fast preservation. Registering all partition I/O is very important in the bottom-up, team-based flow because partitions are compiled at different times, potentially without any knowledge of the other partitions. In a top-down flow, this still may need to be managed. If you cannot register both inputs and outputs, you should at least register one or the other. Most choose to register outputs, as this is considered a good design practice, but this is up to you. The next recommendation is to minimize the number of paths crossing partition boundaries. Remember that these paths will not be automatically optimized by the compiler. Minimizing cross-partition paths reduces placement restrictions between partitions, which is particularly important for timing-critical inter-partition connections. Non-critical connections may be okay, but should be minimized if possible. In the diagram on the left, there is a partition boundary between A and B. This is not an ideal location because the boundary occurs after an expansive function, or a function that generates a large number of outputs from a few inputs. On the right, the partition boundary between A and B has been moved, and registers have been added. This is a better location for the boundary, as it occurs after a non-expansive function, minimizing the number of connections between the partitions to only a single signal. The boundary registers help to meet timing across the path between the partitions. If splitting up the logic into two separate partitions is not possible, an alternative solution could be to add a wrapper file around A and B. Next, let's look at the basics of logic lock regions, since they too are required for fast preservation. Again, if you are already familiar with the creation and use of logic lock regions, including associated routing regions, you can skip to the next section. Recall that a logic lock region is a physical area of the device floor plan, where logic assigned to that area must be placed by the fitter. There are a number of options that make up a logic lock region assignment, such as the basic size and location of the region. However, to use the fast preservation feature, logic to be recompiled must be placed in a logic lock region with all the options listed here. The core-only assignment excludes I/O block resources that happen to be located within the region. In Intel Aria 10 and Stratix 10 devices, I/O blocks are located around the edge of the device as well as in I/O columns in the middle of the die. With the core-only option, regions can span across these columns without any issues. The reserved option tells the compiler to only place logic explicitly assigned to the region in the region. For fast preservation, preserved logic from elsewhere in the design cannot and should not be placed in the region to recompile. The reserved option prevents this from happening. The size and state assignment is used to indicate that the exact size and location of the region is set manually instead of letting the fitter select it. The placement region assignment is the main assignment for a logic lock region. By defining the size, location, and logic assigned to the region, the placement region assures that all assigned logic is placed within the region. Finally, a routing region assignment forces all routing used by the logic in the placement region to be located within the specified routing region. A routing region must be located and sized large enough to at least contain the placement region, but it can be sized larger to account for additional routing required for the region. You can create a routing region by clicking in the Routing Region column in the Logic Lock Regions window. In the dialog box that appears, select the routing region type and, depending on the type, the size and location of the region. The Fixed with Expansion option automatically creates a routing region located around the placement region and extended beyond the placement region by the amount specified in the expansion length option. With a placement region that's sized as 40 by 20, the routing region shown in the example here represents a routing region with a fixed expansion of 1. Use of this type is recommended. It's important to note that even though the routing for logic assigned to a region is constrained to the routing region, routing from the root partition or the PR static region is free to go through the routing region. This avoids having to route around the region, potentially helping to close timing for the top level. Logic lock regions are managed in the Logic Lock Regions window, accessed through the Assignments menu. One way to create new regions is by double-clicking the New cell. Set the width, height, and origin, and enable the reserved and core-only options. New regions created in this way have the region name column displayed as unassigned, indicating that no logic has been assigned to the region yet. Double-clicking Unassigned opens the Node Finder, allowing you to select the logic to assign to the newly created region. Non-rectangular regions, indicated with custom shape in the width, height, and origin columns, are created by selecting multiple adjacent regions, right-clicking, and selecting to merge the regions together. In the example shown here, the logic lock region is set up correctly for use as a region that can be recompiled faster with the fast preservation feature, with logic assigned to the region, the reserved and core-only options enabled, the size and state assignment set to fixed locked, and a routing region assigned. The final things to know before looking at fast preservation in detail are the root partition design reuse flow and the use of project revisions. As mentioned earlier, to use fast preservation, the design must be a PR design or PR-like. If it's a PR design, that means you start with a project set as a PR base revision, where the static region containing periphery resources is created, and PR partitions and regions are defined for base persona logic. If it's not a PR design, you start with what's referred to as a developer project. Similar to a PR base revision, you create the periphery design and define core partitions in the developer project. However, you don't need to include any PR-specific requirements, such as the region controller IP or freeze logic. For each entity in the design hierarchy that is to be recompiled quickly using fast preservation, that entity must be specified as a non-preserved design partition in the PR base revision or developer project, as well as in any PR implementation revisions or consumer project or revisions. For PR, one or more implementation project revisions are required to compile the different personas each PR partition can switch between while maintaining the logic in the static region. For a non-PR design, you need what's referred to as a consumer project, which performs a similar function, maintaining the root partition logic. The consumer project can take the form of a completely separate Intel Quartus Prime project or as an additional project revision of the developer project. Using revisions simplifies project management since only a single project is required, but it limits sharing of the consumer project with other designers. Choose the project management setup that works for you. If you are not creating a PR design, the root partition reuse flow is required for the fast preservation feature to work. As the name implies, root partition reuse allows you to reuse the top-level I/O interface design of the developer project in a consumer project or revision. It is very common to create and verify the I/O interfaces of a design to be able to start board design as soon as possible. Once the I/O interface design is complete, there is usually little need or reason to change it. This makes root partition reuse ideal for use as a starting point for multiple projects that use the same FPGA device and the same board interface, but each one has its own custom core logic. The targeted device must be identical for both the developer and consumer projects, because the root partition design will be unique to the periphery resources and resource organization for the specific device selected. As mentioned, the root partition reuse flow requires floor planning. This is necessary to isolate the custom core logic design from the periphery, which may make use of some core device resources. Floor planning provides a dedicated area on the chip for the custom core design that will be optimized through fast preservation, while still providing full access to the reused periphery interfaces. With these block-based design concepts in mind, let's now look at how to set up and use fast preservation. To use the fast preservation feature with a PR design, there are 6 basic steps listed here. Steps 1 through 4 are typical for a PR design, so making use of fast preservation in a PR design is simply a matter of enabling the feature. Once you set up a project for the feature, you'll only need to keep performing step 6, optimizing and recompiling the non-preserved core logic in each implementation revision to make use of the feature. Here are the similar steps for a non-PR design. In this case, once the project is set up for the feature, you'll be optimizing and recompiling the non-preserved core logic in the consumer project or revision. To get started, create a developer project for a non-PR design or a PR base revision for a PR design. The only difference is specifying the revision type as a PR base revision in the project settings as shown. Create the periphery design and the core logic design, which would be the base persona logic for a PR design, following the design partition recommendations discussed earlier. Of course, for a PR design, you would also need to add PR IP blocks and freeze logic to the static region design in the base revision. See the PR documentation and training linked at the end of this training for details. Next, create design partition and logic lock region assignments for the core logic to be optimized. To do this, perform at least the first stage of compilation, analysis and elaboration, to establish the project hierarchy. Design partition types should be set to reserved core, following the root partition reuse design flow, or reconfigurable, following the PR flow. Each partition to be optimized should then be assigned to its own logic lock region. Optionally, for a non-PR design, you can create additional core partitions for other parts of the design. You can optimize the logic in these partitions with incremental block-based compilation, or reuse them in another project with the core partition reuse flow. However, these additional partitions will not see the benefit of fast preservation unless they are also set to the reserved core partition type and assigned to their own logic lock regions. To create design partitions for fast preservation, right-click the appropriate instance in the Project Navigator hierarchy view, go to Design Partition, and select Reserved Core or Reconfigurable. Make sure the type is set correctly, the preservation level is set to Not Set, and that Empty is set to No. To easily create a logic lock region for the reserved core or reconfigurable partition, right-click the partition in the Design Partitions window and select Create New Logic Lock Region. In the Logic Lock Regions window, set the appropriate options as discussed earlier. The example shown here illustrates how the logic lock region for a partition to be optimized with fast preservation should be set up. Next, fully compile the developer project or PR base revision. Ensure that the root partition meets timing. Closing timing on the root partition is essential whether you are creating a PR design or not. Once the design is fully compiled and meeting timing, the root partition must be exported, again following the design reuse flow. You can export the root partition as a .qdb file either manually or automatically during compilation. To export the root partition manually after compilation, select Export Design Partition from the project menu. Set the partition name to root partition. Select a name and location for the exported .qdb, and make sure the snapshot to be exported is set to final. Enable the Include Entity-Bound SDC Files option so that any timing constraints that are required for logic in the root partition are included in the .qdb file. You can also have the .qdb file generated automatically during compilation. To do this, enter a .qdb file name in the Post-Final Export File column in the Design Partitions window for the root partition. Without a path, the file will be placed in the project directory. If you don't see the Export File columns in the Design Partitions window, enable them from the indicated button. Now, the root partition design will get reused in a consumer project or a PR implementation revision. First, we'll look at setting up a consumer project for the non-PR flow. Create a brand new project using the New Project wizard. In the wizard, enable the option shown to indicate that a .qdb file is used for the root partition, and point to the exported file created earlier. You may want to copy the .qdb file over to the new project's directory. If you forget to enable this in the New Project wizard, you can do it later in the General Project Settings as shown. With a new project, you'll also need to copy over the design partition and logic lock region assignments from the developer project. This is required to make sure the non-preserved core logic is placed correctly in the consumer project. You can either copy and paste them from the developer project .qsf to the consumer project .qsf, or manually recreate them in the GUI. Copy and paste is recommended to avoid any errors. The root partition is always listed first in the Design Partitions window. it should be pointing to the exported root partition.qdb file in the partition database file column, as shown. Instead of creating a whole separate project, you can simply create a new revision of the developer or PR project. For a non-PR design, this new revision becomes the consumer project in the design reuse flow. While this is required for PR, the choice of new project or new revision is up to you for a non-PR design. Create a new revision in the Revisions dialog box and base it on the PR base revision or non-PR developer design. Doing this automatically copies the design partition and logic lock region assignments to the new revision. For a PR design, set the new revision's type to partial reconfiguration persona implementation. Enable the option to use a .qdb file for the root partition and point to the .qdb file exported earlier. Next, enable the fast preservation feature in the new project or revision. It's a simple switch found in the compiler settings. When fast preservation is enabled, any preserved logic in the root partition or other core partitions with their preservation level set to final are basically hidden from the compiler. The only thing visible to the compiler and analyzed during place and route besides the non-preserved partitions is the interface logic that connects the non-preserved logic to the rest of the design. This focus on just recompiling the non-preserved logic and ignoring the rest of the design is the key to fast preservation and much shorter compile times. The final step is to focus on optimizing and recompiling the non-preserved logic. With a much faster compile time, you are free to implement more advanced or compile time consuming optimizations on the non-preserved logic and still be able to perform more testing cycles than previously possible. In the example shown here, a compilation with the feature turned off took almost an hour. Once the feature was enabled, that time was cut by half. As mentioned earlier, once you've performed all the steps for setting up a design for fast preservation, you can continue working and enjoying the benefits of shorter compile times and more design turns per day. If you have multiple floor-planned core partitions that need optimization, you can focus optimization efforts by setting the preservation level for other partitions, whether floor-planned or not, to final. Remember that any partition set to final with the fast preservation feature enabled is not touched by the compiler, saving valuable time. So, in summary, in this training, you saw how to make use of the block-based features and design flows in the Intel Quartus Prime software to set up a design that can take advantage of fast preservation. Good design practices for a block-based flow were reviewed. You learned how to enable the feature and saw the benefits in action through design optimization and shorter recompilation times. To learn about the block-based design flows and features that are required for using fast preservation, register for free for the online trainings linked here. The Block-Based Design User Guide should be your first best source for information about all of the block-based design flows and tool features. The Partial Reconfiguration User Guide goes into detail on everything that is required to implement a PR design. Finally, App Note 899 discusses the fast preservation feature. It includes a downloadable tutorial so you can see how to set up a design for the feature and see firsthand the compile time savings possible. Intel FPGA provides many additional technical support resources besides technical training. Check out the online Intel FPGA forums. They're a great place to connect with other users to share experiences and find solutions to common issues. Use the knowledge base to find solutions to the most common issues you may run into. Manage your software licenses and online training registrations using the Self-Service Licensing Center. Finally, for local assistance, contact your local Intel FPGA sales office to speak with a field applications engineer. One more thing. When you registered for this online training, you should have received a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey now. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this training on reducing compile times with fast preservation.